Is Audie, and I'm going to be showing you throughout these videos quadratic function transformations. In this video, we're going to be going over the y-intercept translations. So, in your equation, a y-intercept translation is going to look something like this. You're going to have y equals x squared. That's your regular parent function. And that's going to change to y equals x squared plus a, plus or minus a, actually, because it can be either, with a being any number. So, for example, let's say that you had y equals x squared plus 3. Now this number right here is going to determine where the vertex of the parabola is on the y-axis. So, for example, your regular parent function would look something like that, right there, with the regular slope y equals x. Now your new slope, or your new graph rather, would look something like this. Since the vertex of the parabola is moving up 3 because you're adding 3, you're going to move up 1, 2, 3 spaces and draw the same parabola with the same slope because nothing changes with the x squared, which is what determines your slope. One thing to mention is if the slope does not change at all in the equation, then that means that both the x and y axes will change, or intercepts. Both the x and y intercepts will change. So, for example, on this problem, the x and y intercept were both at the origin, 0, 0. And in this one, it changed to being no real solution on either, because no, that's not true. It changed to being no real solution for the x-axis, and it moved up 3 to 3, 0 on the y-axis. Let's do another example. So let's say we have y equals x squared minus 1. Draw our same parabola. And this time we're going down 1, so we'll do 1 right there. Same slope and everything, so we're just going to draw y equals x squared, but since the vertex is down 1, your new vertex is going to be 0, comma, up here that was supposed to be 0, 3. Then here it's going to be 0, negative 1. Alright, that is pretty much all that there is going to be to the y-intercept translations. Just remember that this determines where the vertex will be, not necessarily where the y-intercept will be. If you're adding, you move up. If you're subtracting, you move down. Alright, that's all it is for y-intercept translations. The next video will be covering x-intercept translations. Alright. In this video, we're going to be going over x-intercept translations. So these are going to be somewhat like y-intercept translations in that they determine where the vertex is on the x-axis, as opposed to the y-intercept translations determining where it will be on the y-intercept, or the y-axis rather. Alright, so let's say your parent function is going to be y equals x squared. It'll look like that. Now let's say that we make the translation y equals parentheses x. We'll say plus 3 squared. So, in the result, since this is going to be along the x-axis, we're going to be moving our vertex along the x-axis. Now, as opposed to y-intercept translations, adding 3 actually means you're going to be moving left, or towards the negative side. So 1, 2, 3. Which means if we had minus 3 right there, we'd be moving right 3. But it's still the same slope, except our vertex is now 3, 0. Alright, let's do another. We'll do y equals x squared, oops, my bad, parentheses x, we'll say minus 5, parentheses squared. So what that will look like on a graph will be like this. Since we're taking away 5, we're subtracting, we're going to move right instead of left. So we'll go 1, 2, 3, 4, 5 right, and do the exact same slope, because our slope does not change. So that leaves us with our new vertex at 5, 0. Just like the y-intercept translations, do note that this number does not determine where the actual x-intercept is. It determines where the vertex of the parabola is. Oh, another thing is if the slope doesn't change, then the x and y-intercept will inevitably change. So, for example, on this one, our x and y-intercept change from being at the origin, 0, 0, to our x-intercept being 3, 0, and our y-intercept being somewhere up there. Alright, that's basically all that there is for x-intercept translations. They're more or less the same thing as y-intercept translations, except along the x-axis, and the adding and subtracting is flipped. Alright. Next video will be x-intercept reflections. Alright. Alright, hi class. In this video we are going to be going over reflections. So reflections are pretty simple. We're going to be going over x-intercept translations, y-intercept translations, or reflections, I mean, you should not have to worry about. So for an x-intercept translation, your graph is going to change from looking like this the parent function y equals x squared to looking like this. Exactly like it sounds, just a reflection across the x-axis here. And in your equation, that's going to look like y equals negative x squared. Alright, the only real tricky thing with setting up equations with x-intercept translations is combining it with translations or vertical distinction stretches. And I'll explain that in the last video that I do, which is going to go over combining all of these into one equation. I mean, there isn't a whole lot about this, as you can see, well, yeah, I mean, that's pretty much all it is. X-intercept reflections, it's just a reflection over the x-intercept. It's pretty self-explanatory. In the next video, I'll be going over vertical stretches and shrinks. Alright? See you then. Alright, hi there class. In this video we're going to be going over vertical shrinks and stretches, which is going to be a little bit harder than the last few videos, topics in the videos. So first, let's think about what a vertical stretch and shrink is. So if you think about it from a vertical viewpoint, if you're stretching something, you're stretching it vertically. So, like that. It's like you're pulling a piece of taffy up and down. Something like that. Now we could add a parabola to that. Let's make the graph normal size again. Remember that the graph itself doesn't stretch and shrink, the parabola does. So what we can imagine is, let's say we have, this is y equals x squared. Now we do a vertical stretch, and our new parabola will look something like that, depending on the factor or the number you use to stretch or shrink it. So, before I get into equations, let's look at vertical shrinks too. So imagine that you're shrinking it vertically. You're pushing it together, like that. It would be like the parabola looked something like that. Now let's make the graph normal sized again. Normally sized. And if this is our normal parent function, y equals x squared, then our vertical shrink could look something like this. It's like you're pushing the graph downward and it's forcing that to spread out. So, it's almost like you're pushing it together on vertical stretches, which makes the vertical, or the parabola, be more vertical. Or you're pushing down here, and it's making the parabola go out that way. Alright, now let's think about what these are going to look like in an equation. So we've got our regular y equals x squared here. That's our regular parent function. Now what they're going to look like with vertical stretches and shrinks is it's going to look like this. Y equals a being any real number, ax squared. So what that would look like is it would look like, well, never mind. For a vertical stretch, like here, your a, actually, your a is going to be greater than 1. Not greater than or equal to. Greater than 1. So let's say you had a 2 there. That would be a vertical stretch. Now, for a vertical shrink, your a is going to be between 0 and 1. So let's say our new a is 1/2. that would be a vertical shrink. So let's do an example. Let's say we have y equals 3x squared. So y equals 3x squared with our normal parent function looking like this. Y equals 3x squared would look like that. Right there. Not exactly, but you get the idea. Now we'll go over here. We'll say y equals 1/3 x squared. Parent function looks like this. And our new graph, our new parabola, will look like this. Like it's being squeezed to the outside. Being forced to go out this way. That's really the main stuff for vertical stretches and shrinks. Yeah, in the next video, we'll be going over putting all of this together into one equation. So what that will look like for the different combinations of these transformations. Alright? Wish me good luck with that. Alright. Hello class. In this video we're going to be going over combinations, which is going to essentially be adding all of the things that we just learned in the previous videos, or reviewed in the previous videos, putting all of those into one equation. So let's start off with a y-intercept translation. Say y equals x squared plus 5. That's our y-intercept translation. Now let's add an x-intercept translation. So in this, it's going to be parentheses x, let's say minus 2 squared plus 5. So your vertical translation is going to still be on the outside of the parentheses, while your horizontal translation will be on the inside, right here. Okay, now let's add a vertical stretch. So we'll say y equals 3x minus 2, squared plus 5. Alright, now notice how the vertical stretch goes on the outside of the parentheses. Or alternatively, if you, well, I'll go over that in the next problem, I guess. Alright, so notice how that goes on the outside of the parentheses. Now, finally, let's add a reflection in. So your reflection is going to go before the vertical stretch or shrink. Or if you don't have one, it's going to go in front of the x. Or no, that's not true. Well, get into this later. Alright, so there you have it. There is an equation that has all of the transformations in it. So we've got the y-intercept translation going 5 up. Going 5 up, we have the x-intercept translation, which, even though we're taking away, we go right. 1, 2. So our vertex is going to be right there. We have 3 as our, we have 3 as our vertical stretch factor, or number. And then we have it flipped over, not flipped over, well, Yeah, basically. Flipped over the x-axis here. Or flipped upside down, really, is what it means. So our regular parent function, y equals x squared, is going to look something like that. And now our new parabola will look like this. Because we have the vertex up, and to the right, so our vertex is 2, 5. We have the vertical stretch, which means that we're compressing in, we're stretching upwards, which means that our graph will be more narrow. And we have the reflection, which I might have messed up on that earlier. We don't actually reflect over the x-axis. We just reflect it from where the vertex is. So we just reflect it. If it weren't reflected, it might look like that. But we did reflect it over that imaginary line. So now it looks like this. Alright, let's do another example. Alright, let's say we don't have an x-intercept translation this time, so we have y equals x squared minus 3. We'll add in a, well, we won't add in a, well, yeah, we won't add in a vertical stretch, or shrink, I mean. Well, I don't care. We'll add in a reflection. Negative x squared minus 3. Yeah, now we'll add in a stretch, or a shrink, vertical shrink. So it'll be negative, because the negative goes in front of the factor. Negative, we'll say 1/2 x squared. Notice there are no parentheses in this equation because we do not have an x-intercept translation, which is what causes those parentheses. 3, so it'll look like this. 1, 2, 3. Here's our parent function. Flip it over that imaginary line, because that's where our vertex is. 0, negative 3. We'll do negative 1/2, because we're pressing down like this, imagining pressing down like this, which is going to force it to look like that, as opposed to looking like that. Alright, we'll do one more. Okay. We'll say we have y equals, we'll do an x-intercept translation. So we'll do x plus 1 squared. We'll add in, well, we won't, yeah, we'll just add in a reflection. So we negative x plus 1 squared. So original parent function will look like this. And our new equation will look like this. We're adding, so we move to the left 1. And we don't have a vertical stretch or shrink, which means we're going to continue with the same slope. But it is reflected over that imaginary line. So it will look like that. Alright, there you have it for basically every combination, or most combinations of quadratic function transformations. This has been Audie teaching you all of this, and I hope this really helps you out with our quadratic function transformations. Alright, bye.